I want to clarify briefly this term minimal surface. A minimal surface is really a surface that locally minimizes its area, which is the equivalent of having zero mean curvature. We'll go over mean curvature in a little bit. This is like a soap bubble, the way it tries to minimize the area that it takes up between the profiles that it's given. There are several different ways of building these. And really, there are two main ones. And one is to use an equation, a parametric equation or an implicit equation that defines a mathematical object that has been studied and discovered. And the other way is to relax a mesh. When you relax a mesh, it is not really a minimal surface. It's sort of an approximation of something that appears like a minimal surface, or maybe it has close to zero mean curvature or close to locally minimizing its area. It's really just trying to approximate computationally the behavior of a stretching soap bubble. And so these are sort of undefined, semi-minimal, not mathematical surfaces. They're approximations using many little triangles of something that is close to a minimal surface. So I would like to show you how to do both of those methods. Okay, so I want to clarify the different types of equations. There are many different forms of equation for the same shape. There's explicit equations where one variable, say y, is equal to another variable, an expression for another variable. So those are the types we encountered in high school. Things like this, y is equal to ax squared, which gives you a parabola. So you just plug in a number for x and you get a number for y. Parametric equations are a little different. Instead of having one variable in terms of another, you have both variables, x and y, in terms of an independent variable or a parameter, t. And so that could work in 3 dimensions too. X, y, z, each equal to an expression in terms of some other parameter which doesn't have a spatial dimension. And then the last type is an implicit equation, and those are very difficult to solve for because they simply express a relationship between x and y, but it's hard to know how you would solve for y by plugging in an x. Okay, so this is what that looks like. In the case of surfaces, there's usually two variables, u and v. There might be another variable that does something else, but the parameters, the main parameters are u and v for a surface and t for a one-dimensional thing, a curve. And this is the way that works. There's three equations, one for x, one for y, one for z, each in terms of u and v. And u and v are expressed over a range of values. Say, usually it's 0 to 2 pi. Sometimes it's 0 to pi, sometimes 0 to half pi. 0 to 2 pi is for a complete 360 degrees. And so you basically you plug in a bunch of numbers for u and a bunch of numbers for v, and you get different numbers for x, y, and z, and you plot those points in space. And there are many different places to look up these equations. This is what that looks like in Grasshopper. I'll go through that in a minute. I've given you this encyclopedia of analytic surfaces, which has the parametric equations for many surfaces. And you can also look on Wolfram Math World. And what that would look like is on the Wolfram Math World, you would go here and you would see, you'd go there and you'd look around for a particular surface and you might see something like this. And here are the parametric equations, x equals this, y equals this, z equals this. And there's the range of values. U is, v is between 0 and 2 pi. Oh, sorry, that's not actually correct. It's not between 0 and 2 pi. So if I went to Wolfram Math World, I would see this. I could go to the surfaces here. I could go try to find a surface. Let's see if I can find one. Let me see. Okay, and here, yeah, this is a particular conoid, and here are the parametric equations for that, expressed in terms of r and theta. And you can see them here, one for x, one for y, and one for z. And then if I went to the Encyclopedia of Analytic Surfaces, Here's a different equation. This has got many different surfaces. Here's an equation here. So there's a lot of information about it, but you have to look for the parametric equations. Here's the one in terms of X. Here's the one in terms of Y. Here's the one in terms of Z. So that's how you can plug that in. And usually the domain is from 0 to 2 pi, but it might be something else. So you can try that. Okay. So here is how that works in Grasshopper. If I have a surface, I have basically I've given this a point, an origin. Then I've placed a point here in space, and I've done, I've right-clicked here and gone set one point. And that's just to figure out where it's going to plot these points. And then these are the domains. So here it's 0 pi to half pi. That's this domain. And here it's 0 to 1. That's the other domain. And so that's going into U and going into V. And that's producing a range of numbers for U. There you can see them. And a range of numbers for V. And the part that you would have to change is just this. How many numbers do you want? This, what is the domain? This is the domain for U, and this is the domain for V. And then here are the equations. And if there's an extra variable, you can zoom in here and add it. You can just change the name by right-clicking here and changing the name. So sometimes there's a variable that's controlling the radius or something, and sometimes there isn't. Typically, it's just U and V, but there might be another variable. And if you zoom in, you can add it and change the name. Or if these are not U and V, if they're expressed in terms of R or theta or something else, you can change the name there. And then all you need to do is double click here and paste the expression or write the expression in there. So here's another expression for a Klein bottle and a cross cap that I've given up here. But these equations are for the Shirk surface, which I'm going to go over now. And those you can see they take these U and V values, and then they plot a bunch of points in space like that. And then it tries to make a surface that fits those points. That this is a scaling factor, so I often will scale this up. And then I can go here, right click, and go bake like that. Okay. And if I wanted to change this to the cross cap, I could copy these, paste them in here, copy this one, paste it in there, copy this one, paste it in there. And then it's saying it's not working, and that is because there's these variables aren't named correctly anymore. There's no, if I right click on this, runtime errors, there's no R variable. So I would need to give this an R. Let's just make it 1 for now. And I need to give this an R. Why isn't this one working? Oh, there's also no R. Okay, R. Okay, and now this is making a bunch of points. Again, let's take out the scale. Okay, there's a bunch of points, many points. And it's only doing a part of the surface because the domain is wrong. But if I change this to 2, and I change this to 2, and sometimes I need to go from -2 to 2. This is not pi. So if I want this to be 2 pi, that's why I can plug in the pi. There we go. It's actually 0 to 2 pi. This is if I just double click and type pi right there. Okay, so that is making a bunch of points. Like so, and it's making 80 points for each one of these domains from 0 to 2 pi, 0 to 2 pi. If I change this number, it changes the number of points. That's not relevant. The points all follow the equation. It's only how accurate it is. And then I go over here and I can see it's trying to fit a surface, and I can bake that by right-clicking and going bake. That would give me a different surface. It would give me this cross-cap surface. So typically the domain is from 0 to 2 pi, but sometimes it's not. And when it's not, often you can find that again also in the Wolfram math world or in the insight surfaces. But let's go back. Let's go back in time here to the surface that I wanted to show you. Okay, so the other way of doing this is to use a mesh relaxation, and you can do that in Rhino using Kangaroo, which is this plugin written by Daniel Piker. And the way Kangaroo works is you provided a bunch of goals, things that it wishes could happen, and then each of those goals is expressed in terms of is internally in Kangaroo expressed in terms of um, an energy. And then basically it runs the script many times and checks to see whether the energy is more or less, and it tries to minimize the total energy so that it tries to find a solution through many steps that's close to the one you were looking for. So the way this works is you need to give it a coarse-grained version of the surface that expresses the topology, and it's better if you can do that in it's better if you can do that with four-sided surfaces. Okay, so as simple as possible, expressing the topology with four-sided surfaces. And there are examples of this online. Takes a little practice to get used to doing this. There are examples of it online, and Daniel Piker himself posts a lot very generously. But basically, this is another version of the surface that we were looking at previously. Okay, so if you take this surface and the way this script works, let me um, clear this so it doesn't crash, is it takes a brep and then it converts it subdivides it. So if I put this in here um, and I lock this, takes a brep, which is a poly surface, and it subdivides it um, and makes a mesh. Kangaroo works with meshes. So there you can see the mesh. And if I were to bake this mesh, it would have all these little subdivisions within it. And then it uses another plugin called Weaverbird, which you can download to join them all together. Okay. And then it takes that mesh and it tries to it gets the naked edges, the points, tries to keep those where they are, and then makes all the edges stretchy. And tries to minimize the length of all the edges. And if you hit this, it will restart the simulation. And this has to be hit true. And this is where it runs the Kangaroo script. And then at the end, you can go down here and you can go bake, and it'll make something like that. Okay. So it's sort of tried to stretchify all the things. Right now, the issue with this is the edges are still straight. Okay. So there are, because I constrained all the points on the edges. So there are a lot of ways to deal with also getting curved edges. And they vary in complexity. You can put a curve in there and you can have it spring to a curve, or you can have it only constrained in certain directions. However, the simplest way is just to look at what is the base cell of this and make sure you have enough of it. So the base cell is really that. Let me see if I can do that for you guys in front of you. So it's really, it's going to be just that. And then I just need enough of this so that it's that area. I think that's right. Yeah, that area has enough on all sides that it's going to behave more. I'm gonna copy this down again just to be careful. And then I'm gonna take out some of this stuff. Okay, and I'll join all of that. And then I'm just going to run this, put this B rep in here, run it again, hit restart, go down here and bake this. Let me hide the original, put this on a better layer. Okay, and then what I'm going to do is I'm going to go make this little go mesh split with that, delete that, and there it is. Oh, there's not correct right there in the middle. I need a complete ring to get it to work. Okay. Right, let's go mesh split. There we go. That worked, except this little triangle didn't split, so I can try again. Extract mesh face, split. Drawing these meshes. Right, there we go. Um, like weld mesh, it'll join them more completely to each other. Okay. All right. So there I have that. And then if I rotate this 180 degrees, and this, oh, I should mark my axes and my center point. Control how I am rotating things. Okay. Rotate 180 degrees. Rotate 180 degrees. And then this, let's see if it looks smooth. Yep, looks smooth. We can copy that. Mirror that around here. Copy that horizontally. Copy that. Mirror it again. That's the basic shell of this object. And I can copy that now since it is periodic in this direction and also periodic in this direction. And that is what it means when they say that this is a doubly periodic minimal surface. It means you can copy it in sequence. Right. So that is this other surface. And again, you could shear and apply transformations to that, do it of different sizes, in all sorts of exciting ways.